Now, normally, we are only going to be looking at common emitter mode in this course. Of course, I'm not saying common base and common collector don't have application. There are lots of them, and you'll also find some examples in the book. But for the purposes of this course, we are going to concentrate on the common emitter configuration. So in the common emitter configuration, let's check out what are the transistor characteristics. What do we mean by characteristics? We mean how does the voltage, how the voltage and the current related to each other. So let's first quickly draw the circuit. Base, collector, emitter. This is an NPN transistor that we are looking at. Again, this is just a schematic diagram. In general, of course, we will put some resistances to control the flow of current, etc. I'm not bothering with any of those right now. So let's mark out the currents. There is the base current, there is the collector current, there is the emitter current, and over here in the input is the base emitter voltage, and here at the output is the collector emitter voltage. So first, let's look at the input characteristics. So how does VBE vary with IB as long as everything else is kept constant? Well, this just looks like this. It's like a normal diode characteristic that we've seen before, right? Just across the base and the emitter. And what do the output characteristics look like? So this is now across the collector and the emitter. So VCE versus IC. Now this depends on how much is the base current, how much is IB. So for example, if IB is, let's say, 10 microamperes, this is what it looks like. If you take some higher value, you get this. If you take some even higher value, you get this, and so on. And when IB is 0, you might get this. So now this region at the bottom, can you see this? Yes. This region is known as the cutoff region. And this part over here is called the saturation region. and the flat portion is called the active region. And normally the idea is that you are going to operate your transistor in the active region. What else do I want to cover over here? Right. So as you can see, if I define the change in VCE divided by the change in IC, and in the active region, because that is where we are working, this is very large. Oh, sorry. So delta VCE over delta IC is large in the active region. But what is delta VCE over delta IC? This is the output resistance of the transistor of this circuit that we have built. So the output resistance in this case is very high. Now, in the last a few slides ago, I had defined something called beta, which is IE divided by IB, and alpha, which is IC divided by IE. And alpha was just slightly less than 1, and beta was quite large. Now, I want to qualify that, and I want to call these quantities alpha DC and beta DC. That is when a DC current is applied. Now, what happens if I apply an AC current? Then, of course, these currents keep changing. IE, IB, IC will keep changing with time. And then I define beta AC as the change now, because IE is IC plus IB, and then let me divide by IC throughout. Now IE over IC is just 1 over alpha DC, and IC over here I'll write as IE minus IB. Which is 1 plus 1 over beta minus 1, beta DC. But because beta DC is quite large, I can approximate this and write this as so this gives a relation between alpha and beta. Or I can invert this. Now, in the same way that we wrote IE is IC plus IB, also delta IE is delta IC plus delta IB. And then the exact same derivation follows. And from that, you get the same relations but for the AC alpha and beta as well. Now, in order to operate the transistor properly, you have to make sure that the base emitter junction is always forward biased and the collector base junction is always reverse biased. So you have to make sure that this biasing is done properly. This will also enable you to fix what are the operating parameters needed for your transistorized circuit. So for that, there are various possible ways of doing this biasing. So for example, there's something called the fixed base bias. There is an emitter follower bias. There is voltage divider bias. You have various feedback biases, collector feedback bias, dual feedback bias, etc. So let's just look at a couple of them. Let's start with the fixed base bias. So in this circuit, collector, base, emitter. So I put some base resistance over here. Let's call this VBB. Let's ground this circuit. And I'm going to put some collector resistance over here. And here I'll put VCC. So VBB and VCC are providing the correct biasing to our transistor. Let's also mark out the currents IB, IC, and IE. Now let's apply Kirchhoff's voltage law to this loop. So this says that VCC is equal to the potential difference across RC is ICRC, and then you have the potential drop between the collector and the emitter. And that's it. Then you have reached the ground. So this equation and this equation and equations like this are going to be some of the most important equations that we will see in this course. This is called the DC load line equation. What is the significance of this equation? Let's draw once again those characteristics that we saw, the output characteristics, VCE versus IC. And we had various curves like this. Corresponding to different values of IB. 10 microamps, 20 microamps, 30 microamps, 40 microamps, and so on. Now, if you look at this DC load line equation, this is an equation in VCE and IC. In fact, it's a straight line in these two parameters. And the slope is given by RC. So if you plot this line on this curve, you get something like this. What are these 2 points that I have marked out? When this point over here corresponds to IC equal to 0. And when IC equal to 0, you can see from this load line equation that VCE is just VCC. Let's choose a different color. And this point over here corresponds to VCE being equal to 0, which means IC is VCC over RC. So this point over here is called the cutoff point. This point over here is called the saturation point. Now, when you're doing an experiment of this sort, let's say you have built this circuit, you can adjust the value of VBB and RB to allow a certain amount of base current to pass through. So this IB is under your control. You can choose what IB you want. And on this graph, basically what that means is, suppose I have chosen my IB to be 20 microamperes, which is this curve. Then essentially, I am saying that I am going to be operating at this point over here, because my circuit requires me to lie on this DC load line, and IB has been fixed. So this is the common point between those two graphs, between those two plots. So this point over here is called the quiescent point or Q point or operating point. So whenever I have a circuit, a transistorized circuit, in this case I'm looking at a transistorized circuit in the common emitter mode and with fixed base biasing. Here is how you will decide what the DC load line equation is. You'll get the equation for the line, and then you will choose what the value of IB is. And from these two, you will find out what is your operating point or Q point.